In the field of science, the huge mysteries pertaining to what existed prior to the massive explosion, the Big Bang, have sparked mixed conversations and fascinated thinkers for quite some time. This enormous question tests more than just our ability to decode the universe. It challenges the actual boundaries of human knowledge. Picture yourself at the cliff's edge of existence, examining the colossus, observing and pondering what contents might have existed before our universe was even imagined. The Big Bang event established the beginning of all things, including time and space. But in any case, were you there a moment earlier? In the past, this might have been a state of nothingness, a calm before the beginning of cosmic gathering. And if that's accurate, was it truly nothing? Or perhaps something far more frightening existed before the beginning of time? As we continue this inquiry, we are taken on a journey beyond the visible, guided by science. Insight into the beginning of the universe tests our conscious awareness. Physicist Brian Cox, well known for his investigation into the awe-inspiring universe, suggests that surprises may have existed prior to the massive explosion. He urges us to reconsider our perception of the world and existence. In this investigation, we dissect theories, research, and dazzling insider information that might uncover what happened before everything else. We will explore ideas like self-importance in growth, quantum alterations, multiverse, and dark energy. It's possible that the answers we find might paralyze us, or open new perspectives on our position in the cosmos. Prepare to plunge into the depths of the universe, into a realm that defies imagination and science, amidst the obscurity explored by scientists who once worked in the shadows. We are shocked, sometimes even disturbed, as we investigate what existed prior to the Big Bang and the reasons behind these theories, ones that challenge everything we thought we knew. To consider what might have been before the Big Bang, we must first meticulously examine what the Big Bang was. According to scientists, the Big Bang refers to the moment when the universe became extremely dense and hot, rapidly expanding and causing the growth of all matter and energy. When we look at the universe, there are no observable boundaries. The night sky reveals evidence of this hot beginning through the expansion of galaxies in all directions from the original point. But for what purpose did this occur? Was there a time period prior to this blazingly fast start? The idea of massive expansion suggests there was a time before, although it lacked any semblance of form, a cold, empty, and unorganized state resembling a vast vacuum. Nevertheless, this vacuum was not entirely devoid of energy. It contained a tremendous amount of vitality that fueled the rapid extension of space itself. This phenomenon, called inflation, occurred so quickly that it established the foundation for the future of everything. A part of space expanded at unimaginable rates before slowing down, transforming that energy into particles of matter and the forces we now observe as the Big Bang. But what kind of energy was this? What was the reason behind its use? Why did the universe suddenly expand? Some experts believe this immense expansion resulted in patches of the universe, each with its own set of rules. Imagine a fabric expanding after the Big Bang, endlessly forming tiny air pockets, each one illustrating a different universe, including our own. This idea, known as inflationary multiverse, suggests there are conceivably endless Big Bangs, and innumerable universes like ours, each challenging our perception of the cosmos and leaving us with the inquiry, what else is there? The idea that nothing existed before the Big Bang is speculative. Even if we eliminate all radiation, energy, and particles from the universe, true emptiness still wouldn't exist. Quantum fields and dark energy remain, resulting in an embroidered cosmic tapestry, something, even in its emptiest form. Even if we tried to eliminate everything, these forces would prevent a true void. The universe would still produce new forms of energy. This reality is bewildering to experts, suggesting that actual inertia could be impossible in an infinite universe. Understanding space itself means recognizing constants, rules, and properties that prevent it from being truly empty. Imagine constructing a region with no particles or radiation, only quantum fields and fundamental constants. These would continue to exist. This implies that even non-existence has properties. One such property is known as zero-point energy, representing the lowest possible energy state of quantum fields. Even in this state, particles can temporarily appear and vanish, creating the unsettling reverberation of movement, challenging our concept of a genuine void. Indeed, prior to the Big Bang, there may have been a phenomenon scientists are only beginning to understand. One of the most amazing cosmological theories in use today is the possibility of timeless expansion, that inflation could continue forever. Brian Cox provides an astonishing description of an enormous inflationary multiverse, where infinite universes keep expanding, each with its own Big Bang, like flashes of light in another dimension. Despite inflation continuing, it creates areas that generate numerous other universes. In theory, this cycle could continue indefinitely. This notion of vast, eternal universes creates an enchanting concept, a universe of fractals. Each new universe may develop its own Big Bang, existing as an independent domain unaffected by others. The rapid growth of space makes this hypothesis both exhilarating and harrowing. It suggests a multiverse with no beginning or end, only continuous creation. What if the upsetting truth is that there is no before or after, only an eternal pattern of universes evolving? Quantum field theory suggests that the universe is not simply a collection of objects floating in space, but a complex energy network that fills space and creates everything we observe. These fields resemble invisible oceans containing particles as disturbances or waves. Even in their lowest energy state, the vacuum state, they remain alive. Particles can briefly form and vanish in these regions, leaving behind only a faint memory of their existence. This challenges the idea of a real void. Imagine a universe completely devoid of radiation and energy. Would there be nothing? According to quantum field theory, no. Even in a vacuum, fields can give rise to transient particles. The presence of these fields and forces means the universe is never truly empty. This understanding leads us to ask whether particles, and even matter itself, emerged from this vacuum. Dark energy, a mysterious force currently driving the rapid expansion of our universe, may have existed before the Big Bang. Some theories suggest that the dark energy we observe today is a remnant of a field that existed before our universe formed. Its properties hint at a massive, hidden force that may have managed the inflationary phase, triggering the rapid expansion we now associate with the Big Bang. A troubling question emerges. If dark energy existed before the Big Bang, could it have played a role in forming the universe itself? Perhaps dark energy is not merely influencing our universe, but is the key that unlocks the entire multiverse. Another theory offers an alternative to the Big Bang, cyclic cosmology. According to this theory, the universe goes through countless massive disruptions in the fabric of space-time. If scientists can detect gravitational waves that predate the traditional Big Bang moment, they may uncover clues about what happened before the rapid expansion began. These waves, faint and elusive, act as ancient messengers, potentially carrying signatures of cosmic events from a previous universe or from processes outside our current understanding of time and space. This brings us to one of the boldest and most speculative ideas in modern theoretical physics, quantum gravity and the Planck epoch. This refers to the smallest measurable unit of time, about seconds after the Big Bang, a time so early and dense that the known laws of physics break down. At this scale, quantum mechanics and general relativity clash, and scientists believe that a theory of quantum gravity, perhaps in the form of string theory or loop quantum gravity, may provide answers. If such a theory can be realized, it might not only explain what the Big Bang was, but also what conditions allowed it to occur. Another theory posits that the Big Bang was not the beginning, but a transition, a phase change, much like water freezing into ice. In this view, our universe may have emerged from a higher dimensional reality, like a 3D bubble forming in a 4D space. Some physicists call this the brainworld scenario, where our entire universe is a brain floating in a higher dimensional bulk. A collision between two such brands could have released an immense amount of energy, what we perceive as the Big Bang. Others take a philosophical turn and ask, what does it even mean to ask what came before time? Time, as we understand it, began with the Big Bang. Asking what came before it may be like asking what's north of the North Pole, a question that defies the coordinate system. In this view, our minds, evolved to handle cause and effect, beginnings and ends, may not yet be equipped to comprehend a reality where those ideas don't apply. Still, curiosity drives us forward. We continue to probe the cosmic microwave background, CMB, the afterglow of the Big Bang, for anomalies, cold spots, or subtle irregularities that could hint at interactions with other universes. Theoretical physicist Roger Penrose, for instance, has suggested that circular patterns in the CMB might be evidence of a previous universe, a relic from a cosmic cycle of universes stretching infinitely backward. And then there's the possibility of information being the key. Some researchers suggest that the universe functions like a quantum computer, processing bits of information in an ever-evolving system. If that's true, then perhaps the seed of our universe was not a physical explosion, but an informational one, a burst of encoded laws, principles, and potentials that bloomed into space, time, matter, and energy. In the end, the mystery of what came before the Big Bang may remain just that, a mystery. But every step we take, from studying gravitational waves to refining theories of quantum gravity, brings us closer to the edge of human understanding. Whether we find answers or not, the journey itself is a reflection of what it means to be human, to ask, to imagine, and to search for meaning in a cosmos that may be infinite in both space and wonder. Scientists believe cosmic events, if early-stage waves are ever found, could reveal new understandings of the universe's earliest times. These waves might serve as echoes of the Big Bang, or even from before it. Should they be discovered, they could provide evidence of the universe's previous states. The possibility of discovering gravitational waves in their early stages is one of the most intriguing options in modern cosmology. It might reveal not only the truth regarding the Big Bang, but also provide a glimpse into the cosmic state that preceded it. This theory presents an enticing prospect, locating waves of gravitation that could serve as fingerprints from a universe before the Big Bang. As we continue to explore what might have existed since the beginning of time, we investigate ideas that push the limits of our comprehension, challenging even our most fundamental presumptions regarding space, time, and existence itself. One of the most amazing concepts originates from the realm of quantum gravity, which aims to merge general relativity and quantum mechanics. This merger may, or may not, unveil a unified theory of everything and could offer insights into what existed prior to the quantum Big Bang. According to quantum gravity, time and space are not continuous, smooth entities as we commonly experience them. Instead, they may consist of granular structures. This theory posits that the space-time fabric itself could have originated from a microscopic Planck-scale structure, with tiny quantum fluctuations shaping the universe in ways we do not yet comprehend. From this perspective, what we perceive as a smooth space-time continuum may have emerged from these changing quantum fields. Time itself may have arisen from such fluctuations, suggesting that before the Big Bang, reality might have been governed by entirely different rules, where space and time were incomplete or even non-existent. It is also possible that our universe is part of a vast cosmic landscape filled with potential universes, each with distinct physical characteristics. This idea, based on the laws and constants of string theory, proposes that all fundamental particles are, in fact, incredibly small vibrating strings. Within this framework, there are countless configuration options, and each configuration corresponds to a distinct set of physical laws. The string landscape suggests that our universe might be only one of many, each emerging from its own distinct Big Bang. These other universes could feature different strengths of gravity, alternative dimensions, or even entirely different forms of matter. In this view, our universe is not unique but a single member of a vast multiverse, where each universe develops independently. The multiverse theory offers a hypothetical, yet intriguing, answer to the question of what came before the Big Bang: another universe, arranged differently, possibly resulting in infinite cycles, a continuous loop of creation and destruction without a definitive origin. In addition to this, some theoretical models consider the role of black holes in shaping the universe. One emerging hypothesis suggests that our universe may be the result of a black hole forming in another universe. In this scenario, the singularity at the center of that black hole could have given rise to our Big Bang. This idea is supported by general relativity, which states that a black hole's center is a singularity where the curvature of spacetime becomes infinite, and the known laws of physics break down. The extreme conditions within black holes may foster the birth of new universes. This could mean that the Big Bang was merely the birth of our universe from the singularity of a long-dead black hole. Exploring such concepts necessitates a deep investigation into the very nature of time itself. Some cosmologists believe that time, as we understand it, may not have existed before the Big Bang. If true, then the notion of before the Big Bang becomes meaningless. This viewpoint proposes that time may have emerged from a quantum fluctuation or from an initial state where the distinctions between past, present, and future were non-existent. Such an idea challenges the very concept of causality, which assumes that events occur in a linear sequence. If time did not exist, then asking what came before the Big Bang becomes absurd, as there would be no temporal framework to support the question. Theories of cyclic time, as mentioned earlier, propose that the universe undergoes endless cycles of birth, evolution, and demise. In this model, the Big Bang might represent only the most recent upswing in an eternal series of cycles. Each cycle may differ, evolving in new directions and with different physical properties. In this view, the universe is an ongoing process with no true beginning or end, rendering the idea of before the Big Bang meaningless. The notion that time may be cyclical implies that each Big Bang could follow a contraction phase, relaunching the universe in a never-ending loop. Another line of inquiry into the cosmos's potential nature is the idea of a primordial soup, a dense mixture of bits and fields that existed before the expansion of the universe. This state, filled with quarks, leptons, and bosons at extreme energies and densities, laid the foundation for matter and energy as we know them. As the universe cooled, these particles began to interact and form the structures we now observe. Some versions of this theory propose that the early universe existed in a state of quantum foam, where particles constantly emerged and vanished due to the quantum uncertainty principle. The mechanical properties of this soup could offer insight into the earliest moments of the universe, and, by extension, what existed before the Big Bang. In the end, the question of what came before the Big Bang remains one of science's most profound mysteries. As our understanding of quantum mechanics, physics, and cosmology continues to deepen, new hypotheses will emerge, offering increasingly complex and sometimes paradoxical explanations for a universe we may never fully comprehend. Still, the search for this knowledge will continue to push the boundaries of human curiosity, driving us to explore the very edges of existence. While we may not yet possess the tools to directly observe what came before the Big Bang, advances in observational cosmology are slowly opening new windows into the earliest moments of existence. Instruments like the James Webb Space Telescope and proposed next-generation gravitational wave detectors aim to collect data that could hint at the conditions of the primordial universe, perhaps even revealing subtle anomalies that suggest a pre-Big Bang state. Some scientists are also exploring the possibility of detecting a cosmic bounce, a theoretical phenomenon in which a previous universe contracted before giving rise to our own through a kind of rebirth. This bounce, if confirmed, could support cyclic models and challenge the notion of a singular beginning. In such frameworks, the Big Bang would no longer be the absolute starting point of everything, but a transitional phase in a grander, infinite timeline. Philosophically, the implications of a universe without a beginning are profound. It challenges centuries of thought rooted in the idea of causality in creation. Religions, mythologies, and metaphysical systems have long sought to answer the question of origins, yet science, by pushing further into the quantum and cosmic unknown, is beginning to offer answers that transcend traditional narratives. If time and space themselves emerge from something more fundamental, perhaps from information, as some theorists suggest, then the nature of reality becomes a question not just of physics, but of meaning. What is the role of consciousness in a universe where time might not be linear, where every beginning is just a point in a repeating or infinite structure? Are we observers of a singular moment in a vast cosmic cycle, or participants in something even grander? Even as these ideas remain speculative, they illustrate a powerful truth, that the pursuit of knowledge, even when it leads to paradox and uncertainty, expands our understanding of what it means to exist. And in that pursuit, the question what came before the Big Bang may never be fully answered, not because it is unanswerable, but because each answer leads to deeper, more profound questions.